Okay, AP Stats, we just had this very last page of the packet to finish. And of course, let me tell you, there's a typo in example 1. So let's go ahead and fix this. Suppose you roll a pair, there's 2 of them, a pair of fair 6-sided dice until you get doubles. You can't get doubles unless you roll 2. So all we're doing is taking 2 die and rolling them until we get doubles. So I just keep rolling. Oh, I can stop right there because I got doubles. So let t equal the number of rolls it takes. Show that t is a geometric random variable. Alright, does anyone remember the letters for geometric random variable? With binomial is bins. With geometric, it's BIFs. Alright, so B stands for binary. It's binary if I have a success and a failure. I do have a success and a failure. My success is rolling doubles. My failure is not rolling doubles. Didn't leave you much room. So if I can make sure that I have all possible outcomes within my success and failure, it is binary. Doubles and not doubles. Alright, I stands for independent. It is independent because it's just a pair of die, right? The first roll doesn't impact the second roll, doesn't impact the third roll. So it's binary, it's independent. Are we going until our first success? Yes. It says roll until you get doubles and then you stop. So yes, we roll until our success. And then that last S is same probability of success each roll. Do I have the same probability of rolling doubles each roll? And if so, can you figure out what that probability is? So I'm going to give you a minute. We'll pause the video. I want you to tell me if you can come up with that probability of success of rolling doubles. So think about your total sample space and how many doubles are in that sample space. I went ahead and created my sample space here. I knew that there were 36 possible outcomes because the first die has 6 possible outcomes and the second die has 6. So I do 6 times 6 and I have 36 possibilities. So I listed them all here, rolling a 1 and a 1, a 1 and a 2, and so on. Then I highlighted all of our successes. So the yellow is our success, the white is our failure. So it looks like our probability of success, P, would equal 6 out of 36. I have 6 successes out of 36 possibilities. So let's go ahead and get that as a decimal to simplify things. Well, that doesn't simplify things, so let's get it to a simplified fraction. If I divide both the numerator and the denominator by 6, I get 1 over 6. So my probability of success is 1 over 6 each time, and that doesn't change for each trial. I have the same probability of success. Alright, let's go ahead and find P of t. I'm sorry, P of t equals 3, and then we'll interpret this result. Alright, so P of t equals 3 means I got my success on my third roll. So, if I got my success on my third roll, I had 2 failures before that, right? So this represents my failures, this represents my success. So if my success is 1 over 6, what would my failure be? Alright, hope you said 5 over 6. So let me go ahead and put this in Desmos, and we will calculate. Alright, so I'm going to do 5 over 6 to the second power times 1 over 6. Alright, so I get 0.1157. Alright, so that means that my probability, let me switch back to, why won't this minimize? All right, there we go. This means that my probability of rolling doubles on the third try is 11.57%. All right, in the game of Monopoly, a player can get out of jail free by rolling doubles within 3 turns. Find the probability that that happens. Within 3 turns? All right, so we can roll it on the third turn, we can roll it on the second turn, or we could roll it on the first turn. So we would need to calculate the probability of t equals 1, the probability of t equals 2, and the probability of t equals 3, and then add them up together. We already got the probability of t equals 3. Alright, so let's go ahead and do the probability that t is equal to 1. That would mean I got my success on my first try, so I have 1 success and no failures. So that's just going to be 1 over 6. And 1 over 6 is a decimal, 0.1667. Alright, so I'm going to go ahead and put that here for t equals 1. Alright, now we need the probability that t is equal to 2. So that would mean that I got my success on my second try. So I had 1 failure and 1 success. I don't really need exponents because exponents are assumed to be 1, so this is 1 and this is 1, right? So if I just multiply straight across, I'm going to get 5 on the top and 36 on the bottom. So let me put that into my Desmos app. Divided by 36, I get 0.1389. 0.1389. Alright, so I'm ready to add them all up and get my answer. 0.01, oops, already messed up. 0.1, oh my gosh. Alright, I'm just going to do it on that website. Alright. 0.1667 plus 0.1389 plus 0.1157. Alright, so I get my total. Let me just go ahead and write the notation on the paper. Alright. So I went ahead and wrote it right here to get my final answer. The probability that t is less than or equal to 3 was 0.4213. Basically, I just added up these 3 different possibilities. Alright, I want you to go ahead and try number 2 on your own. Okay, so this one was a little different because we're not finding the probability in part A. Part A, what do you think we're trying to find if we're not trying to find the probability? Alright, I hope that you said the mean, and the key word here was expect. How many invoices do you expect to examine before finding one that begins with an 8 or a 9? So expect, you should have thinking expected value, and the expected value is the same as the mean. So what we can do here, so with the mean, we can go back to our notes on the first page, or we can even start looking at the formula sheet to see where these formulas are. So with a geometric distribution, the mean of x is 1 over p. Alright, so with 1 over p, the only thing I need is the probability of success. So it tells us, according to Binford's law, the probability that the first digit of a randomly chosen invoice, 8 or 9, is 0.097. So I know my mean is going to be 1 over 0.097. So let me go ahead and put that into Desmos. 1 divided by 0.097. Alright, and that gives me 10.3. So within that context of the problem, because remember context is one of the most important things in statistics, I expect to examine 10 invoices before finding one that begins with an 8 or a 9. That's my expected value, 10 invoices. Alright, in fact, the first invoice you find with an amount that starts with an 8 or a 9 is the 40th invoice. Does this result prove convincing evidence that the invoice amounts are not genuine? Well, let's figure out what the probability of finding an 8 or 9 on the 40th invoice would be, because we would expect to find it on the 10th invoice. So this smells fishy, and not good fishy, bad fishy. All right, so the first invoice, so what we want to do is we want to find the probability that t is equal to 40. All right, and I said t because we used t in example 1. I guess we could have used x as well to designate this random geometric variable. All right, so that means I had 39 failures before I had the first success. So according to Binford's law, my success probability is 0.097. So what would that make our failure probability? All right, so our failure probability is 0.903. So that would mean 0.903 raised to the 39th power, because that's how many failures we had. And then we had our one success. So our probability is 0.0018. So when I convert that to a percent, that's going to be 0.18% chance that the 40th invoice is our first success. Does that provide convincing evidence that the invoice amounts are not genuine? Yes, it does. That's a tiny percentage. Now, these questions we're going to get more into in the next couple units. These are like significance testing and confidence interval questions, but I just want to start prompting you to think about comparing these probability numbers in context with the real world. It would be very rare that our first success would be on the 40th invoice, because it's 0.18% likely. That's pretty crazy. But we're going to get into more objective tests later in the course. All right, describing geometric distributions. Tell me, when you see the word describing, what are the 4 words that you think of? All right, I hope you said sock of. S is shape of the distribution. O is any outliers. C is a measure of center, and V is a measure of variability. Remember, with random variables, we don't have outliers because we're predicting what happens after a long-term frequency run. So outliers are not involved in our predictions. So we need the shape of the distribution, the center, and the variability. What statistic do we usually use for center with these probability distributions? All right, we use mean, which is the expected value, and then we use standard deviation for the variability. So, describe the geometric distribution from example 1 above with the dice. So the 3 things I need to address are shape, center, and variability. All right, the shape. Remember, we said that the shape of geometric distributions is always skewed right. We said that in our live session because geometric distributions can go on for infinity, right? So, but the further out they go, meaning that the first success is a crazy far number, the probabilities get lower and lower. Just like with this example right here with the 40th invoice, our probability was tiny. So as our first success number gets bigger and bigger, the probabilities get smaller and smaller. So that's why it's always going to be skewed right. So we would say the shape is skewed right. Obviously, I would like you to add context that this was an actual AP exam question, but I just didn't give you enough room here. But you could say the shape of the probability distribution of rolling doubles, or the geometric probability distribution, is skewed right. All right, the center is going to be the mean. So the mean, we did not calculate, but we know the formula for geometric distributions is 1 over p. So looking back, I know that my probability of success for number 1 was 1 over 6. So I'm going to do 1 over 6 in Desmos. I know it's going to look a little crazy. 1 divided by, and then down here we're going to do 1 divided by 6. Oops, not 7, 6. Alright, so it looks like 6, which makes sense because when I'm dividing fractions, I can actually just multiply by the reciprocal. So that's essentially what we did. Alright. So our mean, or our expected value, is going to be 6 rolls until we get our first success. 6 rolls of the dice. Alright. Our variability, which is going to be our standard deviation. Let's go back to the formula sheet, or you can use the first page of the notes, and you'll see the standard deviation formula for geometric distributions. It's the square root of 1 minus p all over p. We know that p stands for the probability of success. So it looks like we've got the square root of the failure, because 1 minus p is essentially the failure probability, over the probability of success. So I'm going to put my 1 over 6 on the bottom and my 5 over 6 on the top underneath the radical. Let's go ahead and put it into Desmos. Alright, so I'm going to start off by doing my fraction so that I can get a square root in the numerator. And in the denominator, I'm going to do my 1 over 6. And up here in the numerator, I'm going to do my 5 over 6. Alright, it gives me my standard deviation of 5.48. Alright, so what that means is, on average, I would expect that with many rolls of these two die, that our average rolls would vary from the mean by about 5.48 rolls. Remember, standard deviation, you should always see the terminology vary from the mean. That means we're dealing with standard deviation. Alright, I want you to go ahead and try to describe example 2 in the same way, the shape and the center and the variability. Remember to use those two formulas for the center and variability, and then we'll check your work in a second. Alright, so for shape, I hope you said skewed right. The distribution is skewed right because all geometric distributions are skewed right. Alright, for your center, you're using that same mean formula, 1 over p. So the probability here, the probability of success was this. We actually already calculated the mean in part A, right? So the probability was 1 over 0.097, which gave us 10.3. So we actually had already calculated the center, 10.3 invoices. And then this, the variability is that standard deviation. This was the only thing that we hadn't calculated yet. So remember, the standard deviation is the square root of the failure probability over the success. Alright, so I know that I'm going to do the square root of 0.903 because that was our failure probability over the success, which was 0.097. So let's plug that in. So 0.097 on the bottom and 0.903 on the top. And you get 9.80 invoices. So you would expect, on average, with many different geometric distributions, you would expect that your number of success would vary by the mean by about 9.8 invoices. Alright, nice job everybody. I'll post this is the last new stuff for the unit, and the unit test is next week. I'm going to post a study guide graphic organizer, and then I'm also going to post one filled out as well, but try filling out the graphic organizer on your own to get used to sorting through the notes and taking notes. And then compare what you did to my filled out graphic organizer to study. As always, let me know if you have any questions. I'm available all weekend if you need some assistance with the Khan Academy or the College Board, and I will see you next week.